Honorable Sri Dattatreya Abba Patil, Honorable Narendra J. Kade, and all Honorable CDC members of the office bearers of all organizations have given their best wishes for this webinar. Today, our guest of honor and keynote addresser of this seminar, Honorable Professor Dr. Kishore Chikliya sir, Professor, Department of Chemistry, with Narmad, South Gujarat University. Other resource person, Professor Dr. Anil Kirdan, Head of Department of Chemistry, Baburauji Adaskar College, Cage Bid. My colleagues, my colleague, Vice Principal Dr. Ramesh Shinde, Professor Swapnil Aunde, Organizing Committee Convener Professor Varsha Nagargoje, Dr. Mukund Rajpankhe, Dr. A.B. Barure, and technical supporter Mr. and Asep Sheikh. I have an immense pleasure to organize this event for this benefit of a new building, scientists and research scholars and faculties. Dear participants, new trends in chemical science include the use of artificial intelligence and machine learning for drugs, discovery and material development, and development of a new technology for energy and environment challenges, and increasing focus on sustainable and circular chemistry. In 2022, a key emerging trend in chemistry will involve looking at ways to simplify the process and make it easier to create medicines for a vast array of illness at much faster pace. New research has already started to make hypotheses for improvement to the process. Lastly, I appeal the participants to the online throughout these events and take the benefit of the deliberation from experts. I hope that there will be fruitful discussion in this seminar. Thanking you once again, one and all. Jai Hind, Jai Bharat.
Thank you so much, sir. It's really an honor for our college to organize such a beautiful program with such amazing guests, Dr. Kishore Chikliya sir and Anil Kirdan sir. Words are too short to describe their achievements. We are feeling so fortunate to have both here today. I request Poonam Lakhe ma'am to introduce our guest, Dr. Kishore Chikliya sir.
Good morning, all of you. May I audible to you, sir? Thank you, ma'am, for giving me the opportunity to introduce the guest honor of our function. Professor K. Chikliya, sir, was a professor and head of the Department of Chemistry in the Gujarat University of Ahmedabad. He has a total experience of 36 years. He has successfully guided 32 students for the PhD and 70 students for MPhil degree. He has published more than 150 research papers in reputed national and international journals also. His H index is 26 and citations are 2718. He has delivered a number of lectures and invited the talks at national and international conferences. His main research area is development of a bioactive couplable by the various cross-coupling and CH activation synthetic strategies. His group has developed a CH activation protocol including alkylation and olefination and arene-mediated function through the arene carbene and radical to get the various sp3 and sp2 CHNH olefin. Thank you, ma'am.
Thank you so much, Poonam ma'am. To know more about new horizons and trends in chemical science, we would like to call respected Chikliya sir to deliver a speech on topics new horizons and trends in chemical science.
Uh, but madam, just it is visible now. I will scroll it. Don't worry. This slide is visible. Madam, slide is visible.
Yes, sir.
My slide visible.
Yes, sir. Visible.
Is it okay now? Hello. Shall I start
Yeah.
now?
Hello.
Okay. Is it visible now?
Yes, sir.
Okay.
It will
Like
continue.
this. Okay. So, first of all, good morning. Good morning, and to fellow colleagues. Principal sir, madam has given a nice introduction. First of, thank you very much for giving nice
Thank you, sir.
introduction. So with this one, I also take opportunity to thank Baba sir, which university I forgot, Chavan University college is affiliated to uh, which Ambedkar University, Sambhajinagar, Aurangabad, right now it is Sambhajinagar. Uh, I am just sharing, I am discussing some chemistry in front of you. Uh, uh, I shall be talking on some organic reactions where a carbon-carbon bond formation takes place. Friends, when we learn, just recollect the memories. When we learn some of these carbon-carbon bond formation reactions, got some Nobel prizes. In first Nobel Prize of carbon-carbon bond formation was given in 1912. That is a Grignard reaction. Everybody knows Grignard reaction. Second, it was given a diacetyl reaction. Later on, Whitney reaction, olefin metathesis. And these are the reactions, the four reactions. They got a Nobel Prize in the carbon-carbon bond formation reactions. I'm just discussing one point. When we teach the students, we simply say one point, the carbon-carbon bond formation reaction, only we just recollect uh, uh, just like the Friedrich reaction, benzene, CH3Cl, AlCl3, and you're getting toluene. It is a CC bond formation reaction. But we cannot tell this reaction because it is simple electrophilic reaction. I am talking the things regarding cross-coupling reactions, activation reactions, or simply I'm telling one line that is a nucleophilic reaction in a sp2 hybrid orbitals. When we teach the students, simple tell one point, okay, chlorobenzene to phenol is not possible. To make this reaction possible, what we need to go, chlorobenzene to phenol is not possible. But if I want to enter OH group in an aromatic nucleus, I need to go for electron withdrawing group at ortho and para position. What we convince the students, okay, when orthonitrophenol is there, it is converting orthonitrophenol at about 180 90 temperature. Cl is replaced with the OH. Suppose if I have 2,4-dinitrophenol, later less energy, less temperature is given, and Cl is converted to OH. If I have a 2,4,6-trinitrophenol, then Cl is easily replaceable to OH group. So what is the disparity is here? Okay, that electron withdrawing group is there. We simply convince ourselves or we explain to students, okay, electron withdrawing group is there. it helps in writing the resonance structure. And when a compound, more and more resonance structure, compound is stable. These are things what we are doing. But right now, it is a trend that you don't have to go for entering electron withdrawing group. You simply go for activate groups. The to activate these groups, uh, metal is entered inside. Cross coupling, this is going for a transmetallization reaction, and you get the products. So it is a recent trend, and in a industries, they are or in R&D sectors where equilibrium reaction is there, and we are following that path. So to make this reaction, to understand this reaction, we need to go for to understand several reactions. That is a coupling reactions. I'm audible, no, madam? My and screen also seen?
Yes, sir.
Yes, sir.
Okay, good, 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 good. If any interruption is there, tell me. So I'll stop and I will do something else.
Okay, okay,
Coupling
sir.
reaction, yes, please. So coupling
Okay.
reaction is there. So this is a coupling reaction. We simply say one is a homocoupling and one is a heterocoupling reactions. See, my presentation is what? Okay, first, I will tell some of the backgrounds of a CH functionalization reaction, and then I will discuss some of the papers, recent papers, which I have published on based on this one reaction. That is the things only. So one is homocoupling and one is heterocoupling. Homocoupling, we understand for a long time, long back, we understood one reaction. It's a Woods reaction, Glasser reaction, Ullmann reaction. This is the coupling of two identical partners in the presence of a metal. This is we studied in a 11th 12th standard basic reactions. So just see this mechanism. These reactions were discovered when electron was not discovered. Then people used to go for such type of reactions. So what is a trivial way? They simply take the reactions and they got the products. Nobody's thought for it's a one mechanisms, or they don't bother for these mechanisms. So this is a simple reactions Rx plus Na, Rr plus Na. This is Woods reaction. But if we go to the concepts of mechanism, we simply say Rx is there, is simply one bond, halide is there, 6 electrons are there in outer orbital. So simple to understand this reaction, we say Rx plus sodium 0, and 1 electron is shifting from this one R side, there is single electron system, is getting 1 electron. 1 electron vice versa getting from sodium, and Na and R is generated. It is going from back reactions, SN2 reaction, type reaction, and to RX, and we get the R product. So this is a simple mechanism of a Woods reaction, a very basic reaction. Right now, next is what is a Glasser reaction. The Glasser reaction, it is just today we say okay, Glasser reactions modification is what it is of a Sonogashira reaction. But Sonogashira reaction concept came through what? It's a Glasser reaction. So when we simply say RC triple bond H acetylene compound is there, one H is being replaced with what? Halide. This is a Glasser reaction. To understand this reaction, we simply say if copper cuprous iodide is taken, it is going for copper iodide is going for acetylene activates, and here H is replaced with the copper. It is going for oxidative addition or oxidation. C2 NME2 is eliminated and one complex is generated. And this complex, yes, this complex is generated, and a complex is going for reductive elimination, and you get a this is a this product, and with a separation of against copper iodide, that cycle is just going on. Next is what? It is a Ullmann reaction. It is known to all. It is very common, known to all reactions. This is a halide, chlorobenzene, copper, and biphenyl you are getting. So to understand this reaction, we simply, as a layman person, we don't know say any more chemistry, but we simply, as a layman person, we say the halide is there, copper is entered here, Cu0. So it becomes, this is entered here, and it is a going for capturing 1 electron here. One radical is generated, aryl radical. Another radical is there, and both radical combine, and you're getting biphenyl. So to chemical consistency, this mechanism if you see. So this is the mechanism is what? Halide is there, Cu0 is added, so it is oxidative addition. So this is converted to copper, is converted to copper 2 here. So again, the second molecule of copper is because copper is entered here. So this is eliminating as a CuX, and a Cu1 is generated. And This U1 again joined with the X halide compound. So oxidative addition. So copper 1 is there, halide is there. We simply find this halide. So these two electrons are being transferred. So 1 is there, the 1 is becoming what? 3. Halide and this metal, it becomes a 3 oxidative addition. That is Cu3. Next step is simply it is going for reductive elimination and you get the product by Ryle. So in this transformation, you can find that the oxidation state of copper is changing from 0 to 2. This is 0, it was earlier 0 here. And this is a 0, this is 2, and again back to 1. Next is 3, and lastly, it is getting back copper 1. So this is the reaction is changing. Is taking copper is changing its oxidation states here. Next is what? Now I'm talking for a hetero or cross-coupling reactions. Friends, these reactions becomes more popular when Nobel Prize was on Suzuki, Negishi, and Heck was awarded in 2010, and people started more and more focused on cross-coupling reactions. Actually, Heck, on my always all lectures, I used to acknowledge Heck because Heck, see the history I'm telling you, okay, in 72, after award of his PhD degree, the graduation, Heck was a very ordinary chemist. He has not done any palladium chemistry, but he was appointed in Vaccor's laboratory where they used to convert acetyl into acetaldehyde using palladium. So, as a curious chemist, he used to ask his colleagues, "Okay, what is the role of a palladium?" Nobody responded. He studied himself and derived one mechanism. And first he paper published in it 72. People were curious, so shocked at time, okay, what kind of chemistry is developed. And in a consecutive 72 to 78, he's published about more and more papers in a Jackson Jocks. And then his work was recognized in a 2009 and he was awarded Nobel Prize in 2010. So during that time, Suzuki, Negishi, Kumada, Maharshi, uh, Nazaki Oshima, Tiamano Kumada, Normand, and one I haven't mentioned, but it is a Mizroki. He passed away. He was a young chemist. He used to work on these cross-coupling reactions, but because of the cancer, he passed away. So that was left only. But this is a simple reaction, Rx plus Ry, transition metal you are using, and you are getting this is alkane formations. See, I simply tell one point, all reactions, they are brothers and sisters. One Suzuki has taken boron, Nagis has taken zinc, likewise, people kept on changing. But every chemist, they have shown that one path and they have developed a mechanism path. And based on this, which they develop the mechanism. So in these reactions, we simply when find as a basic chemistry, we find here's a metal we are taking, it is going for oxidative additions, Rx. We know this point. All reactions is common feature. Okay, they are going for oxidative addition, transmetal addition, reductive elimination, and you get the product. In this case, metal is there. Metal is subjected for oxidative addition, that is Rx. So here is a oxidation status of metal is changes plus 1. Here M, this is general mechanisms I'm writing here. Okay, this is telling case M is called palladium. Either palladium use nickel, rhodium, copper, etc. Why we say it is a Mg, lithium, boron, aluminum, silicon, etc. And R1, R2 is a alkyl or aryl species or alkene species. But it's this general mechanism. All reactions are proceeding by oxidative addition, transmetal reductive elimination, and you get the product. But next onwards, we will understand basic chemistry, basic reaction is this one, but different metal is changes and the reactions proceeding in different ways. But pathway is very common. Oxidative addition, it changes oxidation state, transmetallation, and this is eliminated, and this is the one complex generated. It is followed by reductive elimination, and you get the product. So this is a long time bar diagram, how the reactions occurred. So I have taken some things from somewhere else, and this is simply a copper was used in 1900 centuries. Then later on, other reactions are developed. This is the simple bar diagram of this one. Uh, how chemistry is developed in during this. What I told you about 72, Heck as first chemist. So this is you can say Koru, Umada, Negishi, Sonogasira, this whole reactions has come here. And it is every mechanism, I mean, this is the basic chemistry. Each steps you need to elaborate or we have to understand very thoroughly. Because as a chemist, suppose I am talking for a Sonogasira reaction. So I need to understand okay, what is the oxidation state of the copper, how copper is converted to copper plus one, copper plus two, and copper three. That we have to understand. And then we can go penetrate inside and inside and we learn the chemistry. So some of the slides, some of the products, some of the importance of metals that I will discuss in the consequent slides. So this is simple C. Just it is a general reactions. What I told earlier. This is the diagram where X, Suzuki, and Negishi and everybody is done. What I told you, they used simple metal and they implemented, they taken metal and they developed their chemistry by what type the oxidation changes and likewise. Like we can simply say, I'm interrupting one point and telling you. Suppose you are going for carboxylic acid group is there where COOH group is there, in which one H is easily replaceable. Likewise, you take aldehyde, and here aldehyde, one H is to be eliminated. It's not possible. To understand this point, we have to go for acidic properties. There is a pK value, pKb value, all concepts you have to find out. And since it is not acidic, for aldehyde, replacement of aldehyde H from a uh, aldehyde H from an aldehyde group, then we are going for Umplong theory. That is a 1,3-diethiene theory we understand that we have to do it. So this is simple modification is done all the times. So in these reactions, Negishi is there. Here's taken a zinc chloride, zinc metal, and the quartic compound. This is a carbon-carbon bond formation reactions. Whereas what I told earlier, it is going for a carbon-carbon bond formation reactions. Still a SN is there. So when SN metal is used, again, we have to go in a ground, okay, and 1s2, 2s2, like that only. Okay, how the role of a p orbital, e orbital is taking place, and they help in going for a cross-coupling reactions in to get a carbon-carbon bond formation reactions. Like Suzuki, boron is there. Very interesting chemistry of boron chemistry. As to understand this Suzuki reaction, because everybody is teaching this reactions, this Suzuki reaction in a classes. To be simply say, okay, Rx is there, metal is entered, oxygen state of copper in metal is changes. Then we develop boron. To understand this boron chemistry, we simply write 1s2, 2s2, 2px, 2py, 2pz. So 4 and 5 excitation, one electron is jump. Again, 1 electron is going from 2s orbital, and then reaction is carried out with a base. So all the electrons are being filled up, and boron cannot sustain more and more negative charge. So that it decouples, it detaches from this nucleus, and you get a cross-coupling reactions, and you get a product. Likewise, Sonogasira also is very interesting chemistry. Copper is there, and where iodine is there, this is one is molecule broken down, and we get a new bond. Likewise, Buchwald, very interesting chemistry. A big nucleophile can be entered in a sp2 hybrid orbitals. That is a Buchwald reaction. That is a CN coupling reactions. So based on this one, these reactions, we find I'm not talking for a cross coupling reaction. My purpose is to tell what is CH functionalization. We simple one line I'm telling you. The chlorobenzene to phenol example I have shown you. Based on this one, I want to show you one point how one benzene couple, and they get a biphenyl. So this concept is known as a CH functionalization chemistry. So to understand CH functionalization chemistry, we need to understand the basic chemistry, then cross-coupling reaction. The cross-coupling reactions are these are cross-coupling reactions. Now we just go for a cross-coupling reaction is also becomes a or it is also becomes a so cross-coupling state functionalization reaction is what it is going for to state functionalization reaction we have to understand. So to understand this state functionalization reaction, we need to study some cross-coupling reactions. These are the cross-coupling reaction. So advancement of chemistry is what? Okay, the cross-coupling reaction concept is also a little bit depleted. Not depleted, but it has we people are going for this state functionalization because of what? Because of uh, this is a cross-coupling reactions are little bit advanced this state functionalization. So we have to find out okay, why we are going for state functionalization. What is the disadvantage of cross-coupling reaction? So we understand here okay, both cross coupling reactions, people are doing right now cross coupling reaction, but more advanced stage functionalization. That's why we have to find out what is the lacuna of a cross coupling reactions. So we simply find that both coupling partners must be pre-activated. Organometallic starting materials like boron, tin, Si, these metals are required, which is very, they are showing, they are preparing very undesired metal byproducts. The introduction of halide or pseudo-halide group itself is not trivial, often requiring several steps and suffering from retroselective problems, as well as secondary issues of generating waste from reagents, solvents, and purifications. The other coupling partner must contain either halide or pseudo-halide. Just I spoke this word. They are important point is what atomic economic concepts. That is the clean chemistry concepts. They are not so getting not providing any atomic economical or clean chemistry concepts, which is more required right now in the current situation. So simply, I'm telling them one point. Your cross-coupling reactions with what? Safe functionalization is simply when carbon is prepared, it has just H and X. If you want to go for these reactions, so I need to go for H is there, I have to first convert to X, then it's going to M, metal, and metal is again reacting with a halide. So elimination of the MX and you're getting carbon-carbon bond formation. You can, this is point you can say. Likewise, this is traditional cross-coupling reaction. And now I'm talking for a direct state functionalization reaction is what? H is there. First, I'm entering a metal. It is going for again metal or halide, and you are getting these compounds. So both either HH or X, metal X, a couple, and you get the product. So this reaction is just I was talking earlier. Okay, this is a benzene, transition metal, and you are getting a CC bond formation or biphenyl you are getting. So what are the features of this reaction? Common feature, okay, proposed state functionalization reaction. So this is PD2 acid is there, RH is there. Simply say, okay, when halide is entered, there is a change in oxidation state. But when this is a simple RH or aromatic H is added, there is no change in oxidation state. Because we simply understand one point, halide is there, oxidation, we can simply say there is a loss of electron, gain of electron, this concept. So when RH is added, there is no change in oxidation state. So this is palladium 2 is there. Again, it remains 2 here only. And this is a crucial step. We can say it is an oxidative addition state. Or we can say activation state. Next step is what? Transmetallation or reductive elimination. Transmetallation. So Rx is there, a metal is going, and R metal is joining. And reductive elimination is there. So R is formation, and palladium, what you have taken palladium 2 is converting again 0. That reductive elimination stage is 0. To reoxidize again, it is converted to PD2, and cycle is just going on. So to understand thoroughly some mechanism, because see, we are an organic chemist, and all organic reactions are sufficed by its mechanism. So mechanism of chain bond cleavage by transition metals. So I'm simply telling one point that the base mechanism can be classified two classes. One is an inner sphere mechanism, which involves formation of a new CA bond, and other is an outer sphere mechanism. I will discuss everything on what is inner and what is outer here. So possible pathways for inner sphere mechanism is what? One is going for oxidative addition, electrophilic substitution, sigma bond metathesis, concerted metallation or deprotonation CMD, and one is a 1-2 addition, concerted metallation protonation, deprotonation, that is CMD we can say, and here is a 1-2 addition reaction. Possible mechanistic pathways for the outer sphere is simple biometric biomimetic CH oxidation and a carbenoid or nitrinoid insertion reaction. Right now, fields friends, those who are young, they are freshers, those who are synthesizing organic synthesis, synthetic chemist, you please find out right now is a trend for insertion reaction where you can go for carbene or nitrogen insertion reaction. It is very hot cake in organic synthesis. So simply just inner sphere. I will discuss all the things for inner sphere and outer sphere both. So first is elements, this one, metal is there, plus RH is there. Is the first going for oxidative addition. To here these reactions, you can see it's a dotted bond is written. Both plus cation is here, This is going for NMX, RH, and one is a one complex related oxidative addition here. One is the electrophilic substitution reaction. Simple reaction here, metal, but one bond is just generated between metal H and halide here. And this going for both cation is generated here, and you are getting this one and these two species you are getting. Another is a sigma bond metathesis. Very interesting point is here. So what is sigma bond metathesis here? The elements, this one, RH is here. So this is going metal R and X is getting eliminated and you get the product. Another is a decarboxylation minus CO2. And here is a concerted metallation deprotonation reaction where LNM and LNM R and rest all carboxylic group is just getting eliminated because the lead carboxylation reaction is a very interesting chemistry where it is going through a radical transfer mechanism. I'm showing my slides, some of the reactions I have done in my research that I'm showing this one. And next is a 1,2 addition reaction. It is a simple 1,2 addition, just like we are going for a 1,2 addition, cycle addition, 1,2 addition, almost 3 additions we are doing, simple like these reactions, 1,2 addition, you're getting element H and here XH. So outer sphere is two only, biomimetic and a metallocarbene or insertion reaction. So that we simply see this one, yes, this one, biomimetic is this is cation, both are getting LMS, this one, and RXH is eliminated here. And insertion is also like this cross-coupling type reaction, and metal plus RXH is generated here. So methods for selective CH bond functionalization. So he simplifying the site selectivity is the next important challenge in front of organic chemists to carry out CH functionalization. There are several factors. So what are the factors? Okay, one is innate electronic properties, intramolecular reactions, directing group strategies. What we are numbers of times we are finding. Okay, what is the role of a electron donating group, withdrawing group? How we determine these reactions? Then selective steric properties, ligand control strategies. The general successful methods for functionalization is what? So one direct CH functionalization, sterically controlled CH functionalization via ionic intermediate and via radical intermediates. So friends, listen to this point. The successful way for achieving site selectivity is a directing groups. We simply these reactions, we simply say, cyclometallation reactions, directing groups either electron donating or withdrawing. It matters a lot in understanding this stage functionalization chemistry. So here in this we say, okay, DG is written as a directing group and FHG is written as a functional groups. So my purpose is to enter a various functional group at this place, this place only, because it is, we can say in the entire species, you find is a sp3 hybridization. And in understand one point, sp3 hybridization is there. It's very difficult to eliminate this one H. That is where I understand this point. Halide is there. We simply say okay, because of the hypoconjugation effect, negative generated, just like SN1 reaction, halide can be eliminated. So in these reactions, what we understand here, the directing group is there. So I'm talking for both, either donating group or withdrawing group, both functions. So in this case here, metal catalyst is there. So this H is there when we are entering some metal. So this metal and metal takes a coordination with the directing groups, and this coordination bond is generated. And here in this case, functional group is there. Metal functional group is to be entered here. So we can say RX. Earlier slide I have shown you RX SA2 single electron transfer reaction where backside attack is taking place. Same reaction takes place of functional group X, and here metal is eliminated as a elimination reaction, and you can enter a functional group here. Friends, this is one concept I like to tell one point. To those who have studied some lithiation chemistries, lithiation. Suppose halide is there, I go for lithiation. The ortholithiation is taking place. You might have studied one point here. OCH3 group is there. Because of the coordination of electron pair on OCH3, they make a coordination with the lithiation and some sigma bond generation is there. That just recollect the memories what a lithiation process takes place. So this is one of the analog of that the reactions is taking place. So in these reactions, stage bond functionalizations, the most successful surgically controlled stage functionalization process is a iridium catalysis of arene or haloarenes with boron reagents to form aryl heterodyl boron esters. So we can simply say iridium is a precursor of catalyst, and they are going for a chelations, and we get the functionalization reactions, and we get a CH bond formation, CC bond formation here. So this is a simple to understand this one previous mechanism. I have just understood these reactions. We have done these type of reactions. Just try to understand this reaction. If this is as simple as a lemon person, forget about R1, R2, R3, you can say it is a tell or what it may be. So what is the H is here? So there are two possibilities we find. Either it generates a cation here or it generates anion. Now that both possibilities we understand. If suppose electron pair is going from H and it generates a minus charge. The H is taking electron pair, so that becomes a cation. And as if this both cation and anion, cation and anion we are getting by both fission takes place, and with two species we are getting that this species is combining and we get a this product only. So likewise, what are the this is the common feature of this reaction. So what are the precursors here? So we can say both reactions, cation and anion, what are the precursors we are taking? The precursors are there. NHR, O methoxy groups are there. Olefin groups are there. SLD compounds are there. This is a butterfly type compounds are there. Hetero compounds are there. So there are the precursors of a carbocation. Likewise, carbon ion is there. It has some electron withdrawing groups like this, numbers of withdrawing groups. And everybody knows this point, donating group and withdrawing group concepts. They are the precursors of these reactions. Now, radical generation. Radical is very interesting chemistry, friends. In this case, we simply see H is here, this one, R is here. So this is a fission takes place where X is getting one radical. This radical is being transferred here and a transfer here to this basis, and we are getting this is H is also like this radical trapping. One radical is generated, another radical is generated, and you are getting bond formation. So to understand this radical chemistry, we simply find here it is a R1 H is here. So there are two possibilities are there: cation, anion, radical, and olefin. So in this reaction, simple say R1 cation radical, R1 free radical. It is going with a other compound that is a radical cation, and you get this product. You see this point. This is radical cation. Anion is there. Again, the radical minus charge anion is here. You are getting a anionic product. Free radical is there. You are getting a one radical coupling reactions here. Olefin, you are getting this compound. And this is a simple functional group chemistry. Everybody, this is very basic and functional group chemistry. Everybody knows these things. Now, friends, next point is a cross heterogeneity coupling. What I told you earlier, H is eliminated and you get the product. So likewise here, one H, one Z is this one. Either Z is equal to either carbon or nitrogen, what it may be, or any heterocycle. That is not a problem. But this both H eliminated and you get this simple carbon bond formation reaction. So what is the chemistry involved here? So this we simply see. This is a simple basic reaction is only this. So to I made this simply my this simplification is I simplified, but explanation is mentioned here. Here, transition metal, organic reagent, mediated, this one bond CX or CN, CP or S, whatever may be. Bond formation involving two different stage bonds or one C and H, X and H are known as these reactions are known as cross deheterogeneity coupling reactions or CDC reactions. And a CDC reaction is shown to function well in the presence of variety of metal catalysts like copper, nickel, uh, this one. One minute. These are diagonal coupling reactions. CDCs have shown to function well in the presence of variety of metals. This one also, this one. This reaction is a faster and more economic approach. And a CC bond formation would be the direct cross coupling between C and H moieties. Next is this example. Again, see, I always like to bifurcate these reactions. This is TH is there, both minus, you can see this one. Either it can go for minus charge is there, oxidant you are ready, metal is binded here, transition metal. You can go for carbocation and radical intermediates. This one molecule. Another minus charge is this one. This is only. But basic compound is this one. This is a CH like this one, CH, both and combine this one. So what is the intermediate steps we are entering? We are going for entering of the metal, radical, and carbocation. So this is a formation CH oxidant, metal is added, other carbanion and CC bond formation is there. Suppose carbocation is there, simple reaction is occurring and you get the product. Carbene nitrine radical is there, you get the same intermediate is generated and you get the product. So this is a what are the features of this reaction? So this is going for metals are first binded here and you get a positive charge here, going for minus H radical and you get one olefin type compound, olefinic compound that is going for nucleophilic reaction and at this place you are getting ionic intermediate generated and you get a nucleophilic reactions. Second point is what? It is a simple single electron transfer reaction. When oxygen is there, simple reactions, above reaction. Only here I have to put one air, oxygen, and here in this case cation, minus H, olefin metalysis, olefin is intermediate generated, going for nucleophilic reactions, and you get a product. So these are the reactions only. And here, this reaction, here I have taken something from heterocyclic compounds where a radical transfer reaction is going on and you get a simple bond formation reaction. Also one heterocycle, and here you can find out the reduced selectivity and you get finding one only. This is a very common thing. Now, building block is to be prepared because see, when we understand this chemistry, we trained, we tinted, we are tempted to synthesize the building blocks. Because right now it is a concept where you have to go for a quantification and a qualification of reactions. So that time, quantifications, or you can say the atomic approach. So people right now are going for one pot synthesis, where or cascade type reactions, where we synthesize the reaction with the building block or any one in API, one single task, one single steps. So this is one simple reaction I have shown here. This is going for X is equal to, you can say, any heterocycle. These are going for FeCl3, give you phosphates, this is radical initiators, and you get these molecules, this bond you are generating. The important point is of what's what, butoxide or any peroxides you are taking, you are getting one radical. And this radical is being scavenged, is being reacted with oxygen ether, and again radical is transferred here. It is transferred here, and you get the bond. Finally, this is Fe2 is Fe3, and you get this one intermediate, one API or a building block we can prepare here. It is a one is a glimpse of one preparation of a building block only. When I will talk some of my reactions, when what type of reactions I did in my for my research students are doing, but that will come to know because it is simple as a one building block, but simple molecule I'm showing you, so that will give some more reports here. So this is a simple carbene coupling reactions. Everybody know that carbene, we have been teaching a Remer-Timmer reaction. The phenol is converted to orthohydroxybenzaldehyde, Remer-Timmer reaction. When we are showing the students okay, what is carbene formation, we are talking for mechanism, how the bond formation takes place. So this concept, I am simply say a carbene formation, how carbene is formed. So we simply say okay, this reactions is oxidative addition, transmetallization, CH bond cyclization, metal is there, and a bare metal, okay, one you are taking some hydroxides. Hydroxides are eliminated, pseudohydroxides are eliminated, nitrogen is generated, nitrogen is generated, this is eliminated, and this is going for carbene. And carbene through which a metal is inserted, going for radical transfer, and you get the product. So this is a simple point. This is all the basic points of carbene reactions I have mentioned. This is just cascade type reactions. So my contribution in cross coupling reactions, I am showing that these are the all basics I have discussed with you. Now I am showing how a research is to be carried out based on this concept. So some of the compounds I have done some of the reactions that I'm telling you. See, friends, when you are teaching the students decarboxylation reaction, suppose benzoic acid is there, and a benzoic acid is going for metal or lime, CO2 is eliminated and you are getting benzene. So likewise, this is a simple the reactions I'm showing very basic chemistry. CO2 is eliminated and you are getting this compound. So decarboxylation reactions, coupling, cross coupling reactions are chemical reactions in which carboxyl group is reacted with organic halide to form a new carbon-carbon bond formation. So these reactions I'm showing here. Okay, this reaction is simple say. Coumarin 3-carboxylic acid. Everybody knows this coumarin 3-carboxylic acid. It is prepared by Pachman reactions, malonitrile, piperidine, and salicylaldehyde. I don't go for preparation, but simple say what chemistry is done that I am showing you. This is also another molecule. This coumarin, I told you, it is a Pachman reaction prepared this compound. This thiazolidinone, everybody knows. Okay, first you go for a skip base, aldehyde, conditional aldehyde or ketone with primary amine, skip base going for thioglycolic acid to go for a cyclization, and you are getting thiazolidinone. So these two pharmacophores I am taking, one coumarin 3-carboxylic acid and one thiazolidinone, and this is to be reactions to be carried out to get. See, important is this only. Yeah, this is a carbon-carbon bond formation reaction. This is simple. Now, friends, I'm telling you, suppose you are going for benzoic acid decarboxylation, everybody can do it. But here we have taken a coumarin because we know that coumarin is a N pi transition. This one C NCO bond, CO bond, N pi transition. Also, it is a very delicate nucleophile nucleus. It can be broken down. So decarboxylations, if you go for a stringent condition, just like lime or like that, so the molecule is nucleus is being ruptured. So keeping this point in mind, keeping all these bonds, all the structure, all bonds and everything kept this one stable, and just go for decarboxylation to go for CC bond formation. So this is one reaction I have done. Simple reaction, what was added, DTPP, this case peroxide, is going for oxidative addition, this oxidation addition, and by this way, it is one radical is generated. This radical, this molecule is this one, this is going for peroxides. So it is taking one complex with a Cu complex. It is just next step is what going for decarboxylation, that is the heating. This is the CO2 is eliminated and a one copper. This point you see, this three, and it's a one. Here is this one, and here two is here. It is being supplied with one radical here. One radical you can see this is a CH3. This is sp3 hybridization. One H of this one is going, and he is going for a generation of a radical. This radical, again this molecule, one radical combined, followed by reductive elimination. A copper 2 3 is there. This is radical. Again, Q1 is generated, and both radical combined, and you get this product. Again, the copper 1 is left. That is going for DTBP. Again, core oxide oxidation as cycle is continues, and you get the product. This new bond is generated. And that is a good chemistry. So this can say that this is a simple molecule. We apply a good chemistry and become the paper publication, a good publication we are getting. Another molecule is this one. When one of the students are always curious. So what they're telling is that this gentleman has done thiazolidinone, so why I don't go for CN type coupling reactions? So one student has done a sulfoxamine was taken, a sulfoxamine decarboxylation. Same concept is decarboxylation, sulfoxamine, and he got a CN.
You
bond type
you
of
expected
as well.
the
And you get this. Pardon? So in this reaction also, yes. I'm audible,
Yes,
madam?
sir.
Okay,
Yes, sir.
okay,
Yes.
okay. So this reaction is what copper Cu2, CO2 is this one, acetic acid is eliminated and copper is inserted here. So COOC going for decarboxylation, carbon dioxide is eliminated, and this COOC is generated back. Again, the radical which is trapped here, sulfoxamine one radical, this radical combined, and you get this copper is changing your oxygen state to copper 3. Again, reductive elimination, and you're getting this one product that is a sulfoxamine. And this radical, this Q1 is there, going for oxidative addition, same reactions are going for. And here, the radical is generated. So we always go for confirming these reactions, either radical is generated is correct or not. So we always taken a one control experiment. So tempo was taken, and we get a control experiment. And in control experiment, we didn't get the products. We see understand okay, these are radical reactions. That's why radical such generated, which is being scavenged by tempo, and we confirm the reaction is operating through radical reactions. So one is a one decarboxylation reaction. We got a thiazolidinone, which is a sp3 hybridization. One sulfoxamine, that is of a sp2. One more reaction we have done, that is of a yes. This is yes. So this is what I thought. Why we cannot go for a CP coupling reactions, because there is also good chemistry. The carboxylations were phosphorus chemistry. We have taken different phosphorus and we tried to go for these reactions. So we got a CP bond formation reactions. So various substrate source was taken for phosphorus and we got CP bond formations. Where also is a good things, a copper catalyzed reaction, environmental benign, one pot reactions, CP. See, my all reactions, friends, are of 1% synthesis only. So see the mechanism is here, copper 1 is there, DTPP was there, and copper, this radical is generated here. This is copper as is and here one radical, both radical combine. So copper is back converting it to copper 3 because radical transfer, and which is going for reductive elimination. And yes, and radical transfer is going on, radical reductive elimination, and you're getting copper 1 and cycle is going on. So this paper is just now, it is 15 days back. Yes, 15 days back, it is accepted in a Synlait. It's a good organic synthesis journal. And it's a DOI has come, but it is a still page number has not come. But it is online right now. People can see it. And if you are interested, I can send one manuscript also. Give it a chemistry we have seen. Next is what, and based on this one, decarboxylation reactions, where it is going for C3 and C4 substitution. Because C3 we have knows, okay, C3, what I have shown you, the substitution takes place on C3 carbon, but there is a possibility of C4 also. That is also some of the things what we have continue on select. You can see this one, it is a open. If you say, I can send a review also, but it is a very good selectivity we have shown here in our review. Now, next reaction is what? We are going for 1,3 CS bond formation reactions. Decarboxylation reaction, some students are working again for this reaction, but it's a 3 papers I have published. So that's why I have shown these reactions. There are more possibilities of this one decarboxylation reactions where we can enter some other active motifs in this as a aromatic nucleus. Another is there CSC bond. Simple, just go for basic chemistry. Chlorobenzene. In chlorobenzene, just I told you about phenol, chlorobenzene to phenol. Likewise, you can go for chlorobenzene to thiophenol, mercaptan compounds. Same chemistry is applied. So this mercaptan compound, how we synthesize enter in an aromatic nucleus, that point I'm going to discuss with you. There is a CSC bond formation. Now this CS sulfur we have entered a simple a waste material, that is a, any dye industry or textile industry, they are using a n number of a sulfur, free sulfur. There is a wrong thing, atomic sulfur. The sulfur we are using free sulfur. We have used and we synthesize these molecules. So this simple see this one. Thioethers are a constitution of the sulfur compounds. Various peoples are going for CS bond formation by using different reagents. Just like they are using for thiourea, sulfonic acid, mercaptan, and one what we are doing right now, that's an S8 rhombic sulfur. They are going for a elemental sulfur, going for CS bond formation reactions. So this is a simple, because we are going for a reaction, we need to go for a literature survey and you find what way, how many people has worked on a CS bond formation, and what work we are intended to do, and what is the novelty in work. So we need to go for a survey. So these are the survey. In 78, some CS bond formation was there. Again, Hartwig, CO workers, engineering workers and workers, they have go for CS bond formation. These are some of the slides. It is a previous history, how people has gone for a CS bond formation and they got the product.
Thank you so much, sir, for your valuable guidance regarding. It will be definitely helpful for us in future. Thank you, sir. Now, I request Poonam Lakhe ma'am to introduce our next guest, Dr. Anil Kirdan, sir.
Hello, may I audible to everyone? Hello, sir.
Yes, ma'am, you are clearly audible.
Our next honorable guest is Dr. Anil Shivajirao Kirdan, sir, who was working as a professor, head and vice principal of Babirauji Adaskar Mahavidyalaya Case. His teaching experience is of 26 years. He has successfully guided 3 research students. Now they pursuing PhD in their field. He has published 36 papers in paper-reviewed journals and conferences. He take part in co-curriculum activities in chemistry at Dr. Bamu University. Also worked as a chairman and member of a different committees of a university. Now I hand over to the Miss Varsha ma'am.
Thank you so much, Poonam ma'am. Now, I would like to invite Honorable Dr. Anil Kirdan, sir, to share his views on new horizons and trends in chemical science. Kirdan, sir, now you continue. Hello?
Sir, you are not audible.
Hello, Kirdan, sir? Hello?
हेलो हेलो हेलो
Hello?
हेलो
Are you
हाँ मैडम
audible?
आवाज येतो का Hello. Hello. I'm, hi, madam. Hello. Hello.
हॅलो
हा मॅडम.
सर
Hello.
नाव युअर
हा आवाज येतोय का?
हो येतोय सर.
हा ठीक आहे शेअर करतो मी PPT.
हा सर.
हॅलो करा ना.
हो सर हो.
त्यांनी करणार ते करत नाही. PowerPoint आहे ना. हा हॅलो.
हॅलो
हा मॅडम.
हा सर.
Kirtan sir, you are not audible.
हॅलो.
हॅलो कीर्तन सर यू आर नॉट ऑडिएबल.
हॅलो.
Kirtan sir, तुमचा माईक ऑन करा बरं.
चालू आहे
हा.
चालू आहे ते शेअर करायलाच प्रॉब्लेम यायला.
कीर्तन सर
हा बोला.
तुमचा माईक थोडस जवळ घ्या तुमचा. ते जे हेडफोन आहे ना त्याचा जे माईक आहे थोडं जवळ घ्या असं.
ऐकू येत नाही.
बोलताना म्हणजे आवाज खूप असं लो येतोय पण लो येतोय. कमी
फॅन
येतोय.
बंद करतो. फॅन बंद करतो.
हो दुसरा एक हेडफोन असेल तर बघा सर.
हा बघतो. हो. सर हॅलो. सेंड करू का दुसरीकडे तुम्हाला
हा
व्हॉट्सअपला?
येतोय
हॅलो.
आवाज तुमचा.
हा PPT
हा
मी तुम्हाला हॅलो मॅडम इथून
हा सर.
होत नाही. मी व्हॉट्सअपवर टाकू का तुम्हाला PPT? तुमचा पोस्ट घेतील तिथून. शेअर होत नाही याचे.
ठीक आहे सर मला करा व्हॉट्सअपला शेअर मी बघते होते काही कडनं.
ठीक आहे ना चालेल. हा तर मॅडम सांगा ना. मोबाईल मध्ये नाही सर ऐका सर घेतली डेस्कटॉपवर तुम्हाला व्हॉट्सअप केली धन्यवाद. नाही चित्र व्हॉट्सअप घेत होतो. झाली तुमची शेअर झाली का पीपीटी? हॅलो हॅलो हॅलो
हा सर.
दिसायला लागली का पीपीटी?
सर एक मिनिट हा, पाहतायत सर.
बर त्यांनी पॉज केलं. दिसत नसेल.
हॅलो.
हा
हा कीर्तन सर, तुमची पीपीटी शेअर होतीये, तुम्ही फक्त हे करा, रीड करा.
हा चालतं चालतं.
कीर्तन सर,
हॅलो हा यायला का?
फक्त पीपीटी ओपन करा.
एक
स्क्रीन दिसत आहे.
हा
स्क्रीन दिसत आहे, फक्त पीपीटी ओपन करा.
पीपीटी ओपन करा.
डेस्कटॉपवर सेव्ह आहे का सर पीपीटी?
हा
डेस्कटॉपवर सेव्ह आहे.
आहे डेस्कटॉपवर सेव्ह आहे सर. शेअर होईल
हा, त्याच्यामध्ये एक ऑप्शन आहे. स्क्रीन म्हणून एक ऑप्शन येतो सर, जेव्हा आपण शेअरला क्लिक करतो तर स्क्रीन म्हणून एक ऑप्शन येतो.
हा स्क्रीन म्हणून आहे का?
तिथं क्लिक
नाही ती आहे ना शेअर आहे.
ओके सर, राईट. हा दिसत आहे सर. राईट, ओके.
सर ते आपोआपच व्हायला चालू कर. ठीक आहे, दिसायली का? बघा तुमच्या वॉट्सअप चालू करा मोबाईल मध्ये.
हो सर.
Today's keynote speaker of one-day national seminar on new horizons and trends in chemical science, Professor Dr. Kishore Chikliya sir, Chief Organizer and Principal of Yashwantrao Chauhan College, Professor Shivdas Sirsat sir, Convener Varsha Nagargoje ma'am, organizing committee members and participants joined online. Myself, Dr. Anil Kirdan, working as a Vice Principal and Head, Department of Chemistry, Baburauji Adaskar Mahavidyalaya, KX. Today, I am talking about green chemistry, preventing pollution and sustaining the earth. Dr. Paul is a father of green chemistry. Green chemistry is the utilization of set of principles that reduces or eliminates the use or generation of hazardous substances in the design, manufacture, and applications of chemical products. Green chemistry seeks to reduce pollution at a source. Environmental chemistry focuses on study of pollutant chemicals and their effect on nature. Green chemistry is about reducing waste materials, hazardous chemicals, risks, energy, environmental impact, and cost. There are 12 principles of green chemistry. We will see one by one. First, prevention and prevention of waste byproducts. Waste unreacted starting materials, solvents, byproducts, discharge causes pollution. This diagram shows the most favored options to least favored options. Firstly, we must have to prevent the unnecessary substances which are produced as byproducts. Then second, minimization, then reuse of the byproducts, recycling of the byproducts, energy recovery, and lastly, a least favorable option, that is disposal of that byproducts or substances. Second principle, maximize use of materials, that is atom economy. A reaction is considered green if there is maximum incorporation of starting materials and reagents in the final product. In an ideal chemical process, the amount of starting materials or reactants equals the amount of all products generated and no atom is wasted. The percent atom economy is calculated by using formula relative molecular mass of desired products divided by relative molecular mass of all reactants multiplied by 100. Here there is an example, oxidation of benzene to malic anhydride. In this method, the mass of benzene, that is 78, mass of 4.5 oxygen, that is 144, the mass of malic anhydride, that is 98. And when we have calculated, that is atom economy, that is 100 multiplied by 98 divided by 78 plus 144, it comes to be equal to 44.1%. It means atom economy is very less in this reaction. Same like in butene oxidation. Second reaction, that is addition reactions, in which diene is treated with dienophile, and in this particular chemical reaction, it is green synthesis because the atom economy is 100%. And in second, that is Claisen rearrangement reaction, also the atom economy is 100%. It means the total number of atoms which are used are formed into the products. Third one, that is minimization of the use and production of hazardous and toxic chemicals. Wherever practicable, synthetic methods should be designed to use and generate substances that possesses little or no toxicity to people or the environment. The synthesis of benzene and glucose into adipic acid. Fourth principle, that is design safer products. Chemical products should be designed to effect their desired function while minimizing their toxicity. With the advancement of technology, the designing and production of safer chemicals has become possible. For example, an unsafe drug is thalidomide, introduced in 1961 for lessening the effects of nausea and vomiting during pregnancy. But children born to women taking this drug suffered birth defects. Subsequently, the use of that drug was banned. Fifth principle, safer solvents and auxiliary reactions or reaction conditions. Many solvents used in traditional organic synthesis are toxic. Green chemistry approach use supercritical carbon dioxide as a solvent. Reactions carried out using ordinary water as a solvent. Ionic liquids are excellent solvents for many materials and they can be recycled without presence of any solvent. 6. That is designed for energy efficiency. Energy requirements of chemical processes should be recognized for their environmental and economic impacts and should be minimized. Way to conserve energy or green method by using catalysts, by using microwave heating, using ultrasound, photochemical reaction using solar energy are some sources. 7th principle, use renewable feedstocks. Most organic compounds used as a feedstock are derived from petroleum, a non-renewable resource. A green approach is to replace these petrochemicals with chemicals derived from biological sources. The refining of organic compounds from these plant-derived materials, sometimes called as biomass, is less polluting than the refining process for petrochemicals. Many pharmaceuticals, plastics, agricultural chemicals can now be produced from chemicals derived from biomass. Raw materials from renewable resources. Paper meal, sludge, agricultural residues as waste wood, and municipal solid waste and waste papers are converted into linolenic acid, which is used as a platform for chemical preparation of different chemicals. Use of shorter synthetic routes. Unnecessary steps should be minimized or avoided if possible, because such steps require additional reagents and can generate waste. First reaction, that is chlorohydrin process. In oldest method, there are 2 to 3 steps for the preparation of propylene oxide. But the greener method, that is titanium silicate and hydrogen peroxide at 40 to 60 degrees Celsius and temperature, that is 20 to 25 bar, converted into polypropylene oxide. That is one of the green method. Overall yield and atom economy will decrease for large synthetic routes. Use catalysts. By the use of catalysts, the need for large quantity of reagents can be avoided that leads to waste stream. By increasing the rate of attainment of equilibrium through lowering the activation energy, catalysts reduce the energy requirement of a process. Better yield and atom economy is possible. Reaction becomes feasible in cases where no reaction is normally possible. Green nanocatalysts like gold nanoparticles, silver nanoparticles, etc. are very efficient in organic synthesis. Biocatalysis using enzymes are also very effective in green synthesis. Next principle, that is designed for degradation. Chemical products should be designed so that at the end of their function, they break down into innocuous degradation products and do not persist in the environment. The problem is encountered mainly in insecticides and polymers. 11th principle of green chemistry is real-time monitoring control for pollution prevention. Analytical methodologies need to be further development to allow for real-time in-process monitoring and control prior to the formation of hazardous substances. 12th and last principle of green chemistry, that is inherently safer chemistry for accident prevention. substances and form of substance used in a chemical process should be chosen to minimize the potential for chemical accidents, including releases, explosions, and fires. For example, in 1984, Bhopal tragedy, methyl isocyanate accidentally released and near about 15,000 people died and many of the injured. The manufacturing plants should be designed to eliminate the possibility of accidents during operation. Microwave assisted reactions in water. Advantages: efficient source of heating as energy directly imparted to the reaction medium. Rapid heating leads to saving of reaction time. Smaller volume of solvent required. Diminishes the waste disposal problems. In the end, we can say that green chemistry is not a solution to all environmental problems, but the most fundamental approach to preventing pollution. Okay, thank you.
Thank you so much, sir, for your valuable guidance. It will be definitely helpful for us in future. Thank you so much, sir. Now, I would like to call Pople Madam for vote of thanks. Good afternoon, everyone. I am here to offer my thanks on behalf of all the teachers. We would especially like to thank Dr. Kishore Chikliya sir and Dr. Anil Kirdan sir, our chief guest, for accepting our invitation and joining us today. Your presence has boosted our energy and your thoughts have inspired us all. Your words have really motivated us. I appreciate our principal, Dr. Shivdas Sinsat sir, and Vice Principal Ramesh Shinde sir for always encouraging and directing us. I also want to thank all of you for joining and helping us to make this day successful and special for all of us. Any event is unsuccessful without a loving and appreciating audience. All people who are attending here deserves many thanks, and thank you Godke sir, our science coordinator, who always support us to work hard and do our best. Thank you all. Today's program is end.